This problem will give us some practice with the transverse shear stress equation. So first let's talk about our setup. We have a rectangular beam here, and it's simply supported. You can see that there is this force F that's acting in a transverse direction to the beam, and this beam has a length of L, which you can see at these two locations. So the force is acting on this beam at a distance L/2 from either end of the beam, and so it's a beam of length L. The cross-sectional dimensions, this beam has a width of B and a height of H, and what we're interested in is this point A. We want to know what is the shear stress at point A in this beam. And if we look over here at this cross-sectional image on this side, we can see that A is located, if we're looking at our neutral axis, which is this dotted line, or centroidal axis, A is a distance h/6 from the neutral axis. So we want to calculate what the shear stress is at point A. So we'll remember that, first off, the equation for shear stress is tau equals V Q over I T. Okay, so the first thing we're going to do is find V. And the way that we're going to find V is just like we did in statics. We'll use a shear diagram to find V. So just by inspection, I won't go through actually doing the force balance. You should know how to do that from statics, but from inspection, we know that we have support reactions of F divided by 2 at each of these supports. So we'll start filling in our shear diagram. Let me put this V so it's out of the way. So this is our shear diagram. So here at this end of the beam, there's a shear force of F/2. We know right at the middle of the beam at length L/2, and there's nothing changing, so that shear remains at F/2 till we hit the middle. Then we're going to go down by F down to negative F/2 on the shear diagram, and then nothing changes till we hit that other support, and that will bring us up F/2 back to 0. Now we're interested in knowing the shear stress at point A, which is L/4 from the right hand side. So this is where point A would be. So we can see that the shear force there is just negative F/2, right? So V we know is negative F/2. Okay, so V has a magnitude of F/2, and that's what we'll use in our equation. Okay, so we've already found the first thing we need in our equation. Okay, now we need to go find what is Q. So we'll remember that Q is equal to the integral of y dA, where dA prime is the area. Let's have this be a different color. So dA prime, we'll remember, is the area above the point of interest, or outside of that point of interest, right? So for us, we know that we're at h/6. So between h/6 and h/2 is that area that we're trying to find. So we could do that fairly simply just by looking at the geometry, but let's go ahead and use integral just to get practice for more complex situations. Okay, so this integral y dA prime will actually be the integral of y, and let's just repeat that cross section so it's easy to see. So again, we had our neutral axis. We're looking at a point that's h over 6 above the neutral axis. So if we're trying to integrate in order to find that area above the neutral axis, then we're going to be integrating from a distance of h over 6 to h over 2. So the top of the beam is h over 2. And then if we're taking integral slices, each differential area is going to be having a width of b and a thickness of dy. Okay, so we can do this integral, and we end up with b y squared over 2, and that's evaluated from h over 6 to h over 2. Okay. Now I'll spare you the algebra. You can work through that on your own just to verify that when you evaluate this integral, you will get an answer of bh squared divided by 9. Okay, so that's what q is equal to. So now we are missing I, and we know that the second moment of area, or the moment of inertia for a rectangular beam with width b and thickness h, is equal to bh cubed over 12. That's something we could derive. Just write out that we know that I is bh cubed over 12. And then finally, in the equation for our shear stress, we need that beam width, and that's going to be, that's that lowercase t in the equation, and that's equal to b. Okay, so now we have everything we need to solve for the shear stress at that location A. So we can plug everything in now. So tau is VQ over IT. Which is equal to V. Remember we said that that was minus F over 2, right? Q, we calculated above, is BH squared over 9. And then over I, which is BH cubed divided by 12, thickness T, or B, sorry, T is equal to B. Now you notice I've dropped the sign. Our shear force V was negative F over 2. For now, I'm just going to calculate the magnitude of this shear stress, and then you can get the sign if you're drawing a stress element kind of by inspection. We'll look at that in the future. But for right now, we're just getting the magnitude of the shear stress, so we're not going to worry about the sign on that shear force. So at this point, we just simplify our algebra, and we'll end up with our shear stress at point A. So we'll just say at A, or shear stress, is equal to, after we simplify the above fraction, we have 2/3 F over BH. Okay? And that's our answer. That's how you use the shear stress equation.